So let us begin and let's discuss the next topic, which is damped oscillations. Okay, so till now we discussed oscillations which are undamped. Okay, so we didn't consider any effect due to the medium. So now let's suppose that we have the spring block system. Okay, so this is a spring whose one end is connected to this rigid support, its other end is connected to a block, and it is kept in some viscous medium. Okay, it is kept in some viscous medium. So this medium is there which will oppose the motion of the block through the medium. Okay, and this will cause damping. This will cause damping. Okay, so see what are all the forces that we have. So first one is the force due to the spring. Okay, the restoring force due to the spring, and we know the restoring force is given by, let's call it F suffix R or F suffix S for spring. It is equal to minus of K multiplied by X. Okay, then we have some force, some opposing force due to this medium also, right? So we have some opposing force due to the medium also. That force is known as damping force, and this damping force opposes the motion of block. So it is directly proportional to velocity of the block. Okay, but with negative sign. So F suffix D is the damping force, and it is directly proportional to the velocity. Okay, but it's directed opposite to the velocity. So it is equal to minus of some constant B. B is called as damping constant. So damping constant multiplied by velocity. Velocity. Okay, this is the damping force. So we can say at any given time, the net force acting on this spring block system, the net force is given by Fs plus Fd. Okay, so net force, I'm sorry, we can write it as mass multiplied by acceleration. So it is mass multiplied by acceleration, and it is equal to what? Minus of k into x minus of b into v. Okay, then we can divide this whole equation by m to get a equals to minus of k by m into x minus of b by m multiplied by v. Okay, and then we can put acceleration equals to d2x by dt square, and v is equal to dx by dt, right? V is equal to dx by dt, and a is equal to what? D2x by dt square. So we get this d2x by dt square is equal to k upon, sorry, minus of k upon m into x minus of b upon m into dx by dt. Okay, we can move these terms on left hand side. So we get d2x by dt square plus b by, I'm sorry, b by m multiplied by dx by dt plus k by m multiplied by x is equal to 0. So we got this differential equation. Okay, and this is known as differential equation of damped harmonic oscillator. Okay, this is known as the differential equation of damped harmonic oscillator. Oh, I'm sorry. This is differential equation of a damped harmonic oscillator. Okay. And on solving this equation, we'll get some solution. Okay. So we get this kind of a solution. X is equal to a multiplied by e raised to minus of b upon 2m into t into cos of or sine of some omega dash t plus phi. Okay, right? So we get this solution. And what is this omega dash? So omega dash is the resultant angular frequency of oscillations. Okay, and it is equal to square root of k upon m minus b upon 2m square. Mhm. See, now because of damping, the frequency of oscillations is changed. It is not square root of k by m. Now there is this extra factor. Okay, so omega dash is the resultant frequency of oscillations, resultant angular frequency, and it is equal to square root of k upon m minus this factor. Okay, b by 2m square. Okay, so sometimes this thing is written as omega dash is equal to square root of omega 0 square minus delta omega square. Sorry, not delta omega, we'll write it as gamma. Okay, so see, what is this b upon 2m? B upon 2m is the factor, okay, with which these oscillations go on decreasing with respect to time. See, if we think about the amplitude of these oscillations, amplitude is not constant now. Amplitude is given by what? A dash is equal to a multiplied by e raised to minus b by 2m into t. Okay, we can write this as a multiplied by e raised to minus gamma times t. This gamma is this thing, b upon 2m, right? So it is the multiplicative factor of time in this exponent. Okay, so see, the amplitude is not constant, it goes on decreasing, exponentially with respect to the time. Okay, and by what factor does it decrease? So this is the factor. Okay, this is the exponent, e raised to minus of gamma t. Gamma is b upon 2m. Okay, so this is the resultant frequency and this is the resultant amplitude. So how will the graph of displacement with respect to time look like? So if we plot the graph of displacement with respect to time for this graph, for this damped harmonic oscillator. So the graph will look like so on and so forth. So you can see amplitude of these oscillations is decreasing. Amplitude is decreasing. I'm sorry. Okay. So this graph is not, of course, drawn to the scale, but it will decrease like this. It decreases exponentially like this, right? So this is the graph of x versus t, and it is given by this equation. X is equal to a multiplied by e raised to minus gamma t multiplied by cos of omega dash t plus phi. Okay, so is this thing clear? Next one is post harmonic oscillator. Okay, and we are interested in a particular type of force because it is simplest one. It is external periodic force. Okay, external periodic force. Okay, so see first harmonic oscillator. So what are all the forces acting on this harmonic oscillator? So first one is, of course, we have spring force, right? So it is given by Fs is equal to minus of Kx. The next we have the damping force. So damping force may or may not be there. Okay. I mean, in reality, all mediums are somewhat viscous. Okay, so somewhat damping will be there in all kinds of mediums. Okay, but the damping force can be very, very small so that we can neglect it. Okay, so damp force, I'm sorry, not damp force, damping force equals minus of BV. This can be present or it can be very small so that we can neglect it. Okay, but on top of that, there is external periodic force. External periodic force. Okay. So let's call it FEXT, EXT for external, and it is equal to some F naught multiplied by cos of F naught cos of omega dash t. Okay, plus phi. Okay, omega dash, or let's call it omega E. Let's suppose E for external. Okay, so now what will happen? Okay, so now if you try to write down the equation of motion, okay, then you can write the sum of all forces is the total force. So the net force is given by what? It is F equals to Fs plus Fd plus F external, right? Then we can just like the previous case, we can write down the differential equation for this kind of motion. Differential equation will be like this: d2x by dt square plus k upon or b upon m multiplied by dx by dt plus k upon m multiplied by x is equal to f naught upon m multiplied by cos of omega e times t plus phi. Okay, so this is differential equation, quite difficult to solve, right? But after solving this, we'll get some solution. Okay, we'll get some solution. Now, see, we are interested in a particular case here. Okay, in our NEET exam, this is somewhat difficult thing. So there won't be many questions based upon this. Okay, a specific case we need to understand, and that is the case of resonance. So, what is resonance? What is resonance? So, see, resonance is specific case when the natural frequency of oscillation of a body, it matches with the frequency of external periodic force. Okay, it matches with the frequency of external periodic force, then the body begins to vibrate with very high amplitude. Okay, it begins to oscillate with maximum possible amplitude, and this phenomenon is known as the resonance. This phenomenon is known as resonance. Okay, and if we plot the graph of, okay, if we plot, sorry, if we plot the graph of the amplitude of oscillation versus the frequency, Then see, the graph will look like this. It's a bell-shaped curve. Actually, we plot amplitude square versus frequency. So it is a bell-shaped curve. And so what is this frequency? This is frequency of the external periodic force. Okay, this is the frequency of external periodic force. So when the natural frequency of the body, let's call it omega 0. What is omega 0? Omega 0 is equal to square root of k upon m. So natural angular frequency of body, when it matches with the frequency of external periodic force, okay, with the frequency of external periodic force, omega e, let's call it, then the amplitude of oscillation is maximum. Okay, amplitude of oscillation is maximum. So this thing, this frequency, okay, it is known as the resonance frequency. This frequency is known as what? The resonance frequency. Okay, and then you have two more frequencies here. So this is amplitude square, the maximum value of amplitude square, and this is half of that value. Okay, this is half of that value. Half would be somewhere here. So there are two frequencies corresponding to half of amplitude square. So let's call them omega 1 and omega 2. So these are known as half power frequencies. Okay, these are known as half power frequencies. Okay, so omega 1 and omega 2 are known as what? Half power frequencies. Right. What happens at these frequencies? The power of oscillations, it becomes half. Okay, so this will become more important when we discuss LCR circuits, okay, in alternating currents. Right now, let us just call them half power frequencies and let's leave it here. Okay, so yeah, this is resonance. So what is resonance? When the frequency of external periodic force matches with natural frequency of body, okay, body begins to vibrate with the maximum amplitude. The body vibrates or oscillates with maximum amplitude. Okay, so this phenomenon is known as resonance. Okay, so this is called resonance. Right. So is this thing clear till now? Yes, no. All right. So now, okay, there are two types of vibrations of body. We can say one is free vibration. So what would be free vibration? If there is no external force, body vibrates with its natural frequency. So that kind of vibration is known as free vibration. And when there is external periodic force, then the vibration of body under the external periodic force, it is known as forced vibration. Okay, so these are just some terms. Let's consider a simple example of resonance. So let's suppose this is a string. It is clamped between two supports. This is a support on left, this is support on right. Okay, there are two rigid supports and there is a string clamped between those two supports. So we attach some pendulums to this string. Okay, we attach some pendulums. So let's suppose this is first pendulum. Okay, this is second pendulum. This is third pendulum. This is fourth pendulum. Okay, so this is first, second, third, fourth. So let's call this one pendulum A. This is pendulum B. This is pendulum C. This is pendulum D. Okay, so now see, we know that the frequency of oscillation of a pendulum depends on length of pendulum only. Okay, or time period of oscillation is 2 pi square root of L upon G. If we want frequency, it is 1 upon 2 pi square root of G upon L, right? So natural frequency of oscillation of A and C is same, okay? But A and B, A and D, they are different, right? And since the frequency is inversely proportional to root of L, the frequency of oscillation of A and C is more, right? So frequency of oscillations of A is equal to frequency of oscillation of C, okay, but it is more compared to that of frequency of B, and it is more compared to the frequency of D, right? FB is also more compared to FD, right? Okay, FA and FC are they are greatest. So now you take this pendulum A, you give it a little bit a push, small push, and release it. Okay, so now it oscillates like this. Okay, you pull it like this and release it. So it will oscillate like this. Okay, perpendicular to plane of the paper. Okay, or your screen. So what happens? This is known as driver pendulum. Okay, the first pendulum that you are setting in oscillation, it is known as driver pendulum. Okay, others are known as slave pendulums. Okay, so what will happen now? So all these slave pendulums also, they will begin to vibrate. Okay, they will begin to oscillate, and so out of these, which one will oscillate with the greatest amplitude? Out of B, C, and D, which one will oscillate with the greatest amplitude? So it is pendulum C. Reason? Because the natural frequency of oscillation of C is equal to the natural frequency of oscillation of the external force. Okay, what is external force? Okay, it is force exerted by this A, pendulum A, when it oscillates, right? So the natural frequency of C is equal to what? Natural frequency of the driving pendulum. C will oscillate with maximum amplitude. The other two, they will oscillate, okay, comparatively lesser amplitudes, right? So this is the phenomenon of resonance. So every communication, it is based on the idea of resonance. Okay, so for an example, uh, if you take an example of FM, okay, so FMs have particular frequencies, right? Okay, there is, I don't know what are FMs operating there. There is one Radio City. Okay, Vivid Bharati would be there. Vivid Bharati, right? Prasar Bharati or Vivid Bharati, I don't know. Okay, Radio City is there, Radio Mirchi. What are the FMs operating in Tamil Nadu? Radio Mirchi is there. Okay, there would be some others also. Okay, Radio Mirchi, Radio City. So all of them, they transmit at some particular frequency, right? So Radio Mirchi, for an example, it's here it's 93 point something, 93.1, okay, megahertz. Okay, then this is suppose Radio Mirchi. Then other one is radiosity, okay, 95.5. So they transmit at this particular frequency, at a particular frequency. And now what happens when you tune, okay, when you tune, you means what? Your FM, okay, FM receiver, whatever it is, a mobile or dedicated FM, okay. So when you tune it, what happens it changes the capacitance, okay, it changes the capacitance of LCR circuit. So there will be some LCR circuit, we'll learn about that in alternating current, okay. But it changes the frequency of receiver in order to match the frequency of this transmitter, okay. And when those two frequencies match, then your receiver, I'm sorry, receiver receives the signal. So what does it mean by receives the signal? It begins to oscillate with maximum possible amplitude, okay. And this is the phenomenon of resonance, right? So this is an example of resonance, okay, in real life, what we use in real life. So FM communication, cellular communication, okay, TV broadcasting, all of them are based on resonance, okay. Then have you heard that soldiers, okay, soldiers, they are asked to break the steps when they travel, okay, when they are moving on a bridge or something, okay. So when soldiers cross a bridge, so whenever they walk like this, left right, okay, this is their marching. So they are advised to break the steps of marching, okay. Why so? It's because if all of them march with the same frequency, okay, in unison with each other, what might happen? Okay, what is the worst thing that can happen? That the natural frequency of vibration of that bridge, it will match with the natural frequency of their marching, okay. That is the natural frequency of external periodic force, and then the bridge can collapse, okay. The bridge can collapse if this thing happens, okay. So there was an example, sorry, there was an incident when bridge literally collapsed, but not because of the marching of soldiers, it's because of the periodic winds, okay. The name of that bridge is Tacoma Bridge, okay. So you can search this, you can watch this video. So literally the natural frequency of oscillation of the bridge matched with the blowing wind there, okay, wind that was blowing there. So the bridge got collapsed, okay. And it happened within few months. It was very huge bridge, okay. So you can watch this video, and then you will come to know how devastating this phenomenon of resonance can be. Suppose there is a closed hall, okay. Suppose there is a closed hall and somebody is singing or performing something, and the crowd is cheering in unison with each other, okay. So the frequency of cheering crowd, if it matches with natural frequency of oscillation of the roof, then roof might collapse. But this is very rare thing to happen, okay. But it might happen that the frequency of cheering of crowd, it matches with the frequency of oscillation of roof. So the roof might get collapsed. So these are some of the examples of resonance. So let us solve some problems now, some simple problems. When an oscillator completes 100 oscillations, it, its amplitude reduces to one third of initial value. What will be its amplitude when it completes 200 oscillations? Okay. So this is simple. See, now within 100 oscillations, it reduces to one third of the original value. After 200 oscillations, what will happen? It will reduce to one third of one third, right? Okay. This is another 100 oscillations, you can say. Okay. So it will reduce to one third of one third. That is 1 by 9 is the answer. You can solve this if you like. After some time, what happens? Okay, so let us write down an equation of amplitude of damped harmonic oscillator. So A at some time t is equal to A multiplied by e raised to minus b upon 2m into t, or we can just write minus gamma t. Okay, gamma is called as decay rate. Okay, see, now after 100 oscillations, so t is equal to what? T is equal to 100 times t. What happens? You get amplitude equal to a by 3. So a by 3 is equal to a multiplied by e raised to minus of, okay, 100 gamma capital T. So you want to find what happens when t is equal to what? 200 times t, right? So it is a at that time is suppose 80, it is e raised to minus 200 gamma t. Then you can divide these two. Okay, so actually this thing and this thing gets cancelled. It is 1 by 3 equals to e raised to minus 100 gamma t. Okay, so you can write 3 is equal to e raised to 100 gamma t, right? So 3 equals to, or e raised to 100 gamma t equals to 3. Okay, and you can substitute that here. Okay, so I can say 80 upon a, or let's write a upon 80 is equal to e raised to 200 gamma t. Okay, or this is equal to e raised to 100 gamma t square, that is 3 square, right? What is 3 square? 3 square is 9. Okay, so a upon 80 is equal to 9, and that means 80 equals to what? A upon 9. So option D is the answer. Next question. In case of a forced vibration, the resonance peak becomes very sharp when the option A, damping force is very small, damping force is small, restoring force is small, applied periodic force is small, and quality factor is small. Okay, what is quality factor? Actually, it is F naught divided by 2 times delta F. What is delta F? Delta F is the particle with restoring force proportional to displacement and resisting force proportional to velocity is subjected to a force F sine omega t, right? So there is restoring force proportional to displacement, that is minus kx, and resisting force, which is damping force, it's proportional to velocity, minus bv. Okay, it is subjected to this force. This is the external force, external periodic force F sine omega t. If the amplitude of particle is maximum for omega equals to omega 1, and energy of particle is maximum for omega equals to omega 2, okay, then omega naught is the natural frequency of oscillation of particle, right? So what will be the answer of this? Omega 1 is not equal to omega naught, and omega 2 equals to omega naught. Omega 1 is equal to omega 0, and omega 2 equals to omega 0. Omega 1 equals to omega 0 and omega 2 is not equal to omega 0, or omega 1 is equal not equal to omega 0, omega 2 not equal to omega 0. Tell me what will be the answer. So this is simple actually. Amplitude is maximum at omega 1 and energy is maximum at omega 2. So what is energy? What is energy in SHM? Half of Ka square. Sorry. Okay. So when amplitude is maximum, then only energy will be maximum, right? When amplitude is maximum, then only the energy will be maximum. Okay. So amplitude is maximum at omega 1, right? And energy is maximum at omega 2. So these two frequencies must be equal. Yes, no? Okay. And resonance will happen when natural frequency matches with the frequency of external periodic force, and therefore it should be equal to what? Okay, the frequency at which amplitude becomes maximum and energy becomes maximum, it should be equal to the natural frequency of oscillation of the particle. All right, next question. So there were very few questions in NEET exam based upon resonance, based upon damped harmonic oscillator, and also on forced harmonic oscillator. So we'll discuss some questions from some other exams. Okay. So the equation of damped simple harmonic motion is this thing. We know this equation: m d2x by dt square plus b dx by dt plus kx is equal to 0. Then the angular frequency of oscillations is. So this thing, you know, it is direct question. Tell me what is the answer. Okay, this frequency we have to remember. Omega dash is equal to what? Square root of k by m square. Sorry, not k by m square. K by m minus b upon 2m square. Okay. So what's the answer? So option A, right? So let's see next question. In case of forced vibration, the resonance wave becomes very sharp when. Okay, this is copy pasted from the NEET exam only. Okay, so it's option C, when damping force is small, right? Next question. During the phenomenon of resonance, the amplitude of oscillation becomes large, the frequency of oscillation becomes large, the time period of oscillation becomes large, all of the above. Which is the answer? Okay, option A is the answer. But second and third, if frequency becomes large, then what will happen to time period? It will become small, right? So both cannot be large at the same time. So, okay, this is contradictory, right? But in resonance, so resonance is defined with respect to amplitude only. The amplitude becomes large, okay, that is phenomenon of resonance. Let us see next question. If differential equation is given by, this is the differential equation, d2i by dt square plus 2k dy by dt plus omega square y equals to f naught sine pt, describe the describes the oscillatory motion of a body in dissipative medium under the influence of periodic force. Then the state of maximum amplitude of oscillation is a measure of. Tell me. Okay, it's measure of Resonance, maximum amplitude, right, happens in resonance. Let us see next question. The amplitude of damped oscillator decreases to 0.9 times its original magnitude in 5 seconds. In another 10 seconds, it will decrease to alpha times its original magnitude, where alpha equals. Okay, so see, again, we'll just think about it. Okay, we can solve this question by a little bit of thought only. No need to solve it actually. Okay, using numerical calculations. So see, in 5 seconds, what happens? It becomes to, the amplitude decreases to 0.9 of the original value. So in another 10 seconds, so another 10 seconds means twice of 5 seconds, right? 2 times 5 seconds. So another 5 seconds, what will happen? It will become 0.9 of 0.9. In another 5 seconds, it will become 0.9 of this thing, 0.9 square, right? And then we just need to solve this. So it is 0.9 cube, or 0.9 multiplied by 0.81, we can say. Okay, 0.81 multiplied by 0.9. 729 is the answer. Right, option C. Okay. Okay, let's see next question. The displacement of a damped harmonic oscillator is given by this equation. Here t is in seconds. Time taken for its amplitude of vibration to drop to half of its initial value is close to. This is from JE. Okay, it's a simple question. So this kind of question can be asked in NEET also. Right. So x of t is equal to not 0, e raised to minus zero point 0.1 t multiplied by cos of tan pi t plus phi. Okay, so what is amplitude? This is the amplitude, right? So amplitude is given by e raised to minus 0.1 t, and this becomes half. It drops half of its initial value. So how much is the initial value? Put t equals to 0. Okay, so anything raised to 0 is 1. So this thing raised to 0 is 1. That means initial value is 1, right? Okay, there is no other multiple here, right? So put t equals to 0, this thing becomes 1. So that is the initial amplitude. Okay, so at some time, what happens? It becomes half. It becomes half. So half is equal to e raised to minus 0.1 t. So therefore, we can say 2 is equal to e raised to 0.1 t. Okay, what I have done is I have changed this to positive. So we have to take reciprocal of this thing. 2 equals to e raised to 0.1 t. After that, we have to take log of this. Okay, but it will be which log? Natural log, right? So ln of 2 is equal to log of this. Okay, ln of e raised to 0.1 t, and 0, okay, this is anti-function, the log and e raised to something, okay, exponent and log. So therefore, you can write this as 0.1 t, ln of e is 1. And then you can convert this to log to the base 10. Okay, we can convert this to log to the base 10. How come? So it is 2.303 multiplied by log to the base 10 of 2. We'll just write it as log of 2. 0.1 t, this thing multiplied by log of 2. Okay, and we have to remember log of 2. Okay, because it will come here, it will come in uh, radioactivity also, right? So log of 2, okay, we should remember, it will be handy. So log of 2 is 0.3010, okay. So 2.303 multiplied by 0.3010 is 0.1t. We can move that 0.1 on left hand side, okay. So it becomes this thing multiplied by 10. So this thing multiplied by 10 is equal to t. So how much is t? This thing 2.3 times 3, okay, 69, right? 0.69, 0.69 or 6.9, 6.9, sorry. So t equals to 6.9 seconds, right? So it is option B. Let us see next question. A damped harmonic oscillator has a frequency of 5 oscillations per second. The amplitude drops to half its value for every 10 oscillations. The time it will take to drop to 1 by 1000 of the original amplitude is close to. Okay. So, see, damped harmonic oscillator has frequency of 5 oscillations per second. So its frequency f is equal to 5 hertz. Okay, and its amplitude drops to half its value for every 10 oscillations. I'm sorry. So see, every 10 oscillations it drops to what? Half its value. Okay, T is equal to 1 upon f. Okay, so every 10 oscillations, what is happening? Its value is dropping to half. Okay, so can we say that time taken for, so then the amplitude drops half its value every 10 oscillations. Okay, so in every second it performs 5 oscillations. Okay, so how much time will it take to perform 10 oscillations? 2 seconds, right? So for t equals to 2 seconds, its amplitude drops to half of its value. So then the time it will take to drop to 1 by 1000 of the original amplitude. Okay, so this is given that a by 2 is equal to a into e raised to. So let's write our equation. At equals to a multiplied by e raised to minus gamma t. Okay, so a by 2 is equal to a multiplied by e raised to minus 2 gamma, right? When t is equal to 2 seconds, amplitude becomes half. Okay, so this thing gets cancelled, a and a gets cancelled, so we get 1 by 2 is equal to e raised to minus 2 gamma, or 2 is equal to e raised to 2 gamma, right? We can say this. After that, what do we want? We want the time when amplitude becomes 1 by 1000 of the original value. So a by 1000 is equal to a multiplied by e raised to minus gamma t. Okay, so a and a gets cancelled, so we get 1 by 1000 equals to e raised to minus gamma t. Okay, or 1000 is equal to e raised to gamma t, right? So then what can we do? Yeah, we can take log of this thing itself. Okay, so if we take log of this thing, so ln of this 1000 is equal to ln of e raised to gamma t, and from that we get gamma t is equal to what? 2.303 multiplied by log to the base 10 of 1000 is 10 raised to 3. right? So we can write, sorry, multiplied by 3 multiplied by log to the base 10 of 10 is 1, and that's equal to gamma t. Okay. Then from this equation, what do we get? We get ln of 2 is equal to what? Ln of e raised to 2 gamma. Okay. So this thing can be written as 2 gamma is equal to ln of 2, or 2.303 multiplied by log of 2. Okay. So 2 gamma, we can substitute for gamma here. Okay. So substituting for gamma, what do we get? 2.303 multiplied by 3 is equal to, gamma can be written as, okay, half of this thing. So half of 2.303 multiplied by log 2 multiplied by t. So this 2.303, 2.303 gets cancelled. 2 can be taken on left hand side, so it is 6. Okay. So t is equal to 6 divided by log 2. And how much is log 2? It is 0.3010. Right. So what is, we can say round figure, it's 0.3 only. So 6 upon 0.3. 3 multiplied by 10 raised to minus 1. You can take that 10 raised to minus 1 in numerator. So it becomes 10 raised to plus 1. So 6 upon 3 is 2. 2 times 10. So it is 20. So t equals to 20 seconds. This is the answer. Option C. No, it's not option A. Option C is answer.